speaker is Carlos Martinez-Bazan from University of Granada.
Thank you. Okay, thank you. First, I would like to thank Mark, Sasha, Jose for inviting me to be in this workshop, the interesting workshop. So let me just start with my presentation. It's going to be about the modeling of the breakup and coalescence of bubbles. This is a work that most of the work has been done in collaboration with Patricia Ern and Veronique Ross from the Institute of Fluid Mechanics in Toulouse, and has been mostly done by Javier Ruiz-Ruz, right there from the University of Jaén. I mean, you already know why bubbly flows are important. Bubbly flows are very relevant in many engineering applications and natural processes, right? The gas in liquid provides a surface through which mass is exchanged. So leading processes in two-phase chemical reactors, heat exchangers, cleaning tanks, and many others. It also drives the ocean atmosphere exchange of CO2 by the air entrained by breaking waves. So it's really important to provide like reliable models to be able to describe the evolution of the population of bubbles in a flow. In this case, it will be in a turbulent flow. The problem can be simplified by studying the behavior of an invisible fluid immersed in a liquid flow, a turbulent flow maybe, where we can describe how the population of bubbles, I mean, if the turbulent stresses acting on the surface of these bubbles are larger than the confining stresses due to surface tension, the bubble will break, and we'll try to describe the evolution of this population of bubbles that is formed, right? The problem was already studied a long time ago in the early 50s by Kolmogorov and Hinze. They provide with a maximum bubble diameter, that's a stable bubble diameter that was able to remain unbroken in a turbulent flow. That's the maximum bubble diameter is called usually the Hinze diameter, and it's just the diameter such that the confining stresses due to surface tension are of the same order of the turbulent stresses acting on the surface, right? But the important thing here is to be able to describe the time evolution of the population of bubbles that is formed there, right? And this is what we try. So, so the description, the talk will be, the outline of the talk will be what is shown here. First, I will describe the population balance equation, which is used to describe this evolution of population of bubbles. To be able to solve the population balance equations, we need models for the breakup and also for the coalescence of bubbles. So I will describe some models that we developed a long time ago and the latest work in the coalescence of bubbles in a flow. Right? The population balance equation is nothing but it's a transport equation that describes the time and the spatial evolution of the population of bubbles in a flow. In this case, N is the probable number of bubbles of the volume V in a given position at a given time. V is the mean velocity of bubbles of the given volume, which are at the same position at that time. And QC and QV is just the rate of change of this population of bubbles due to coalescence and due to breakup. And this is what we need to model to describe this evolution. The breakup rate has two terms. It has a sink term, and it has also a source term here. The sink term accounts for the number of bubbles that break and is given by the breakup frequency of these bubbles. And this is something that we need to model. And the source term accounts for the number of bubbles that are generated due to the breakup of larger bubbles. This is why we have here M, which are the number of bubbles that are formed when a bubble breaks. F is the population of bubbles, the Dota bubbles, the Dota bubbles probability density function, and G is the breakup frequency. So we need models also for the breakup frequency, this number of bubbles, and the Dota bubble size distribution. And the same for the coalescence rate of. We have also a sink term, which are the accounts for the number of bubbles that die or they disappear because they coalesce to form a larger ones, and a source term that accounts for the number of bubbles that are created due to the coalescence of the smaller ones. This is why we have the integration here from 0 to V. In this equation, lambda is just the collision efficiency between bubbles of volume V and V prime. H is the collision frequency of bubbles of volume V and V prime, and GC, which is here, is the coalescence frequency of the bubbles of volume V with any other bubbles. So, and to close this equation, we need models for the breakup frequency, the Dota bubble size PDF, the coalescence frequency, and the coalescence efficiency. And this is the purpose of this talk. So initially, I talked briefly about the coalescence frequency, or the breakup frequency of bubbles, and then I will talk about some experiments and models that we developed to obtain the coalescence frequency of bubbles, or the coalescence. For the models, like a long time ago, for the models for the breakup frequency, a long time ago we performed experiments in a turbulent water jet. Actually, at that time, I was blonde. I was in this gray hair, so it was quite well done. So we injected bubbles in a turbulent jet with the needle, and we follow with recording with the camera. We follow the population of bubbles that they are creating. We have bubbles here, so we are moving upwards. We are moving from the left to right. So we see that the bubbles are broken, and we track the bubbles. We are able to determine the population of bubbles. We go to different positions, and we just obtain the bubble size distribution as they evolve. So we see that initially we have a large PDF here with large bubbles, and the bubbles break and form smaller ones, right? So in this case, since we didn't have coalescence, the equation that I showed before, this equation doesn't have this term, so everything is related to the breakup. So we simplify the equation to just a convective transport of these bubbles due to the breakup. So the equation simplifies to the evolution of the population of bubbles due to the breakup of bubbles and the formation of bubbles due to the breakup of larger ones, right? So if we plot the flux of bubbles, we see that initially the flux of bubbles increases because there is a breakup event, so bubbles are generated because they are formed due to the breakup of larger ones, until eventually they don't break anymore. So we could follow this evolution as the size distribution. So to get the frequency of breakup in this case, what we did, we just focus on the largest bubbles of the distribution, the bubbles that are here. So focusing on these large bubbles, we don't have formation of these large bubbles due to the breakup of larger ones, because there are no larger bubbles, right? So this term will be gone, and we have only that one and that one. So if we focus on the largest bubbles of the distribution, the equation simplifies from here, and we can extrapolate the breakup frequency of bubbles of the volume P. See, and this is what, just measuring the size of the flux of bubbles, the number of bubbles that we have in the distribution. So we plot the breakup frequency of these bubbles versus the dissipation rate of turbulent kinetic energy. So this is the way we obtain experimentally the breakup frequency, and we model it. We we propose a simplified model where we propose that the breakup frequency was just a function of the set of stresses between the turbulent stresses and the confining stresses due to surface tension. So we have here the experimental data and the model, which match very well. But at that point, we proposed that a dimensional model, and later on, we just try to modify the model, just making a dimensionless model. So we can make the breakup frequency dimensionless with the turnover time of the eddies, and basically this breakup frequency, the dimensionless breakup frequency, is just a function of the Weber number of the bubbles. There are many other models provided based on different ideas, and all of them have been given in dimensional form. So when we plot all these models, we have models, I won't go to explain all of them, but we have models from Kologlu et al. Kono et al., Prince and Blanch, with different expressions and based in different ideas. But when we make the models dimensionless with the characteristic time, we see that all of them just collapse on the same curve. So basically, the breakup frequency of the bubbles in a turbulent flow is well captured, is well predicted, right? The only, and we plot that with our experiments, and we see that they all match very well. They only have differences near the critical Weber number with the Souther unity, and it's because in our model we predicted that bubbles whose Weber number is smaller than 1 will never break, and bubbles whose Weber number is larger than 1 will break at a given frequency, which is given by the model. So they only have differences at this nearly 1 Weber number. So that in that case, we are happy with the breakup frequency for the model. It seems that independently of the model that we want to apply, they will probably give the same frequency in dimensionless form. Let's go now to the coalescence to model or the coalescence frequency of bubbles. As I said before, The coalescence rate depends on this coalescence frequency and the collision efficiency and the collision frequency, and this is what we try to model to be able to integrate this equation. To be able to do that, what we did, we performed recently, a few years ago, some experiments in a thin cell gap. So it's a planar gap. It has a thickness of a millimeter, and we injected bubbles from the bottle of the channel, right, from 16 capillary needles of diameter 0.6 millimeters. So we have here bubbles which are much larger than the thickness of the gap. So it's a Hilly cell, basically. And just also recording images with the low speed and high speed camera, we will try to develop models for this collision and coalescence frequency. To do that, what I said, we perform low frequency experiments and high frequency experiments at 250 frames per second. We recorded images at 3 different positions with the cameras. So we injected the bubbles through the 16 capillary needles from the bottom. You see the evolution of the population of bubbles. They are small here, they start coalescing, and they get bigger as we move further downstream. We use 4 different injection conditions, just changing the flow rate of the air. We change the flow rate, the void fraction from 0.4 to 6.7%. And we record, as I said before, images at 4 different positions. Here we see some snapshots of the population of bubbles at different void fractions. You see that at lower void fractions, the bubbles here are basically monodispersed and they start coalescing later on. When we increase the void fraction, the coalescence starts really close to the injection position, right? For the low speed measurements, we just took images at half of a second. This is the recording frequency, just to make sure that the bubbles that are in one of these windows are not in the following one. So we have uncorrelated images. I recorded about 3,000 images, taking between 25,000 and 250,000 bubbles in there. To analyze the data, we just divided each recording region in 5 windows. So we have 15 positions, 15 windows, and from that positions, there were overlapping windows. We were able to get the number of bubbles, the gap void fraction, the size distribution, and etc. Just as a sample, you see here, like for one of these void fractions, you see the color shows the different windows that we are plotting, and here we see the evolution of the probability density function. Initially, we have a monodispersed production of bubbles, and the density function increases as the bubbles coalesce, right? The flash of bubbles is here. For the low void fraction, we see that initially we don't have coalescence, and then the bubbles start to, the flux of bubbles decreases because they start coalescing, and for larger void fraction, the coalescence process starts from the very beginning. So as I said, we also have experiments with high-speed camera. So we took images at different regions with the high-speed camera at 250 frames per second. And we developed, and when I say we developed, Javier developed a bubble tracking algorithm. So this is not a commercial one. It's been done by hand in a couple of years, right? And he was able to track every single bubble in the window and follow it. So we could see it from there. I don't know if you see the images, like the bubbles, when they start, and you see there's a coalescence there, and right there, right? So we could just track the bubbles and see how they evolve. We could get the trajectory, the velocity, and their behavior in the window. And from this tracking algorithm, we are able to get the area or the diameter of the bubble, the position, and the velocity, and also, which is more important, if the bubbles were colliding with other bubbles, and if they collide, if they coalesce later on, right? So you have collision or coalescence effect. So now I can show some of the results that we have there. Just analyzing the data, we realized that instead of working with the population of bubbles, with the distribution of bubbles, we try to get a characteristic diameter. And the characteristic diameter here that we obtain is dV90. dV90 is the diameter of the bubbles, such as the volume of these bubbles is 90% of the volume of the total number of bubbles in the distribution. So this is, and that is a good representation of the largest bubbles in the distribution. So we, instead of showing the results in terms of the distance, the downstream distance, we could show the results in terms of this dV90. So you see that dV90 increases as the distance increases because they are coalescence and the distribution becomes wider. But when we plot the size of the distribution, so the shape of the distribution versus dV90 rather than C, we have, for example, here, you can see that distributions obtained with different void fractions at different positions, they are identical. So dV90 is telling us the number of coalescence events that we get until we get this distribution. And for void fraction 4.9, it will be in a given position, but if that distribution for 6.7 will be earlier because they have the same number of events at the shorter distance. So that's what dV90 is relevant here. And also it will be used also to characterize the characteristics length and the characteristic velocity given by the velocity of these bubbles. When we plot the flux of bubbles in terms of this dV90, so you see here that we have the flux of bubbles, and this dV90 divided by the initial size of the bubbles, the flux collapses on the same curve. So it follows. So this is a good characteristic diameter to work with the model. So now from that, I said we need to get results for the collision frequency and also the collision efficiency. The collision efficiency was easy. We just calculate the collision efficiency by the number of collisions that ended up in the coalescence, and we could follow the bubbles, so we could track that, divided by the total number of bubbles. In our experiments, we see that this collision efficiency is about 80%, independently of the gas wave fraction, the position of dV90. So we have a very high rate of coalescence just because our configuration is planar, right? So the bubbles cannot escape due to three-dimensionalities. So from now on, since we have the same collision efficiency, I will talk about coalescence frequency, or collision frequency is the same because this is a constant number. So to just obtain the collision or the coalescence frequency, as I said, we track the bubbles, follow them, and see they collide with other bubbles and coalesce. So to get a good statistics, we just divided the bubbles in different classes or different diameters. We follow them and calculate this collision of the coalescence frequency, just counting the number of collisions that ended up in the coalescence and divided by the number of bubbles that we have in a given position, the number of the other kind of bubbles in the same position, and divided by the recording time. So here we have the collision frequency or the coalescence frequency of the bubbles of size k with bubbles of size k prime. So we count the number of collisions divided by the number of bubbles that we have in that window, the number of the other bubbles in the same window, and the time. So we have a direct measurement of the coalescence frequency. So if we just go here on one of these positions, for a characteristic dV90 of the 18 millimeters, we see that the coalescence frequency of bubbles of 4 millimeters increases when the size of the other bubble also increases. If we go to a different bubble, this one is about 5 millimeters, also increases with the size of the other bubble. But as we increase the size of this bubble, we see that now the frequency increases and starts decreasing. Also for larger bubbles, increases and starts decreasing, and increases and starts decreasing. So depending on the size of the bubble that we are considering, we have this this increase of the breakup frequency of bubbles with the size of the other bubbles, or this other behavior where the frequency increases and then decreases. The same result can be shown in this plot, where we have here the size of one of the bubbles, the size of the other bubble, and this color map is just giving us the frequency of the collision. So that, and showing the same plot for the different positions, we saw the plots that they show the similar patterns, and we realized that this collision or coalescence frequency is just a level curve of what we call the reduced diameter. So the reduced diameter is nothing but the diameter of the bubble whose curvature is the mean curvature of the two bubbles that they are interacting. So we have that the collision or the coalescence frequency is just a function of this reduced diameter of the. In fact, when we plot all these curves versus dp, this equivalent diameter, all the data collapses on the same curve, and it's the same behavior. This one is for that position, but if we go to the other positions, we get the same results. We say that the frequencies of all of them. So in that case, we observe that we have two different regions, right? In the first region, the collision or the coalescence frequency increases with dp, which is over here, reaches a maximum and starts to decrease. So we went back to the video images just to see what happened there, and we could see that in the first region, where the frequency increases or the coalescence frequency increases with dp, the bubbles, let's see, they just go, they meet, and they coalesce, right? It's like in this region, it's a rapid coalescence process. The bubbles, they just meet and they kiss, we say, right? But in the other region, we have there are larger bubbles, and the bubbles, they just get together, they close, they are very close, but they start like dancing before kissing, is what we say, right? And it's because it takes some time to drain the liquid field that is created there. So in that case, it's, in the first region, the collision, the coalescence frequency increases with dp, and the other one decreases. And this is something that we like to model. Here there are some images where we see that the bubbles, they go and they get close, they collide and coalesce. In the other ones, they get closer, but they start just moving around for a while until they coalesce, right? So we have two different. And what we need are models to be able to solve this population balance equation. So in the first model, we try to model this breakup frequency just using the analogy of the kinetic theory of gases. So it's like the collision frequency is going to be the product of the collision velocity times the collision area, right? And we see that the bubbles are, as I said, the bubbles, they just meet and coalesce, right? So they need to be, we have to have like a characteristic velocity, and they have to have within a given distance together to be able to coalesce. So this is the scheme that we have. So these two bubbles, they are somewhere here, and they are moved around due to the velocity fluctuation induced by the population of bubbles, right? We don't have a flow. The flow is generated by the populations of bubbles. So we have like these large eddies, the analogy of the turbulent flow, the large eddies created by the largest bubbles in the distribution, and they need to be within a given distance to be able to be affected by the velocity and coalesce. So we get a velocity which is proportional to the characteristic velocity of these large bubbles that we have seen that they are just leading the distribution. And the distance is going to be also characteristic distance of the divinity with the function of the alpha, right? So, and also we know that the frequency varies with the dp. So when we just get this model given by the characteristic velocity and the characteristic area, when we plot all the data within the first region, it's shown here in these colors, and this is the model. So we have the experimental coalescence frequency divided by the model, and it follows they all collide or collapse in the same curve with this linear trend. So we see that we have a good model for the first region. For the second region, we see that the bubbles, as I said before, they just get together, but they start just dancing around for a while until they coalesce. So they have to deform. This surface needs to be deformed by the strain rate of the liquid that is surrounding them. So we propose that this frequency is going to be the strain rate times a characteristic volume. So the strain rate is going to be just the characteristic velocity divided by the diameter, this equivalent diameter, and the volume is the dV90 squared times the thickness of the gap. So, and when we take these experimental measurements of the coalescence frequency divided by the model that we propose, the data just collapses here. So it seems that we have captured the experiments. But we have a first region where the bubbles, the frequency increases, or coalescence frequency increases with the dp, and the other one with where it decreases. So it has to be like a turning point, right? And this turning point is just if we match the first model with the second model, this characteristic diameter at which the maximum is reached is given by alpha dV90 divided by the thickness of the gap, square root of that. So we plot our experimental data with this simple equation, and the points just follow the same trend. So that's the end. I will probably skip conclusions because it's basically the summary of what I have shown, and just like to thank you, and I hope you guys enjoy the game. Spain, France, I mean, I've seen the bets are like Spain is going to win by 30% times 31 France, so I hope that's right. Thank you.
Are there any questions?
Stefan.
Yes, thank you for a beautiful talk.
Thank you.
I'm thinking that maybe coalescence is a little bit like the bubble bursting phenomenon. You create a thin film between the two bubbles,
Yes.
at least for the large case, and then you have to drain this film.
Yes.
So you should have perhaps a dependence on the falling time by
Yes.
under gravity, the drainage time.
Yeah, I mean, yes, you are right. There's a thin liquid film that has to be drained, but we started trying to model all of this, but I mean, we wanted to have something simpler, that like a theoretical model able to describe that and to be able to go to the population balance equation. And in this thickness, this liquid, now we can do it because, I mean, we can do it for some cases. We have the data. I mean, so we have good resolution. The two bubbles, we can characterize the film, so we know how the film is thickening, right, or thinning. Sorry, so we can measure the draining velocity of the liquid. We haven't done that, and we try to do some like a more phenomenological model for the population balance equations initially. Yes. Thanks.
Thank you.
Thank you for the nice talk.
Thank you.
Also nice to see some experiments. If I do this kind of experiments, the water is typically not clean. I don't know what you're using. So how versatile or how,
the water was super clean. The water was
yeah.
No, it's not,
what is the effect of a different liquid, or
no.
if you do that in oil or in dirty liquid, how does it affect your?
I will expect we'll get
balances?
something similar. In this case, the water was deionized water, right? And we cleaned the tank like every day.
So it was dirty, yes.
It was dirty. Okay, it was dirty. In that sense, it was dirty. It was not ultra pure water.
Repeatable dirty, yes.
Yeah.
So if you use other liquids, how does it affect this balance equation?
I don't know. I guess we will get something similar with oil, right?
Yeah.
So because it was not clean. It was not clean, but I think it was not contaminating. It was not dirty with that. But it's it's the question that everybody wonders. Yeah.
Thanks, really nice talk. Have you then used these models in those population balance equations to see if you get the distributions you
We
expect?
started yesterday. Yes.
Oh, okay.
Yeah. Now we are with Javier. We are applying the model to the population balance equation, and as I said, we have the evolution of the PDF, right? So we
Yeah.
have the answer.
Yeah.
So now we are implementing the model in the population balance equation and see if we get the PDFs that we are measuring. Yes.
Great.
We are
Thank
in that
you.
part. Thank you.
Do you think that if you try to apply the model in 3D, it will be qualitatively similar, or maybe just changing some coefficients, or
It's
very different?
it's different, but I believe personally, I believe that the ideas we can apply that ideas. Obviously, the coalescence efficiency will go down quite a lot, and it's probably a function of the size of the bubbles, because in our case, the bubbles, they just collide and they cannot escape, right? They can just go around, but they don't go to the three-dimensional direction. In a 3D flow, they could escape. So, but these ideas of applying with the characteristic velocity, which is given by the dV90 of the distribution, and this characteristic distance, I think we can apply that's ideas. To do three-dimensional experiments, I don't know how to do that, because you look with the high-speed camera, you are blocking the projection, so it's hard. So we don't know how to do that.
Thank you.
Sure.
Any other questions or no? Well, if not, let's thank Carlos again.
Okay, thank you.